Good afternoon, Southminster Scholars. Before we begin today, I want to give another shout out for the 2020 Southminster Community Fund campaign. One of our Community Fund's recipients is Queen's University Learning Center. On November 17th, the well-known speaker Doris Kearns Goodwin, author and Pulitzer Prize winner, will speak live in the Belk Center, and she will address the 2020 election. Where do we go from here? That lecture will be streamed live on QB. Watch for future information, but whatever you do, save the date, November 17, 2020. Continuing today, we're going to continue with Dr. Summers and learn about the star of our solar system. As we wend our way through the solar system, we will pause today to focus on our sun, which is a star similar to 100 billion others in the Milky Way. The sun, however, is closer to us than most all of the other stars. Therefore, we can interpret the sun more easily than most of the other stars. We're now able to determine the sun's multi-layered structure right down to its intensely hot and dense core. Within that core, nuclear fusion converts enormous amounts of energy. Dr. Summers will today take us on a journey from the outer layer to the core. Keep your sunglasses on at all times during this journey.
How many stars can you see in the night sky? When you look up without a telescope, how many do you think you can see? Most folks will answer millions of stars because intellectually they know there really are millions and millions of stars out there. But if you actually went and looked and tried to estimate, what would you find? Of course, it would depend upon where you were looking. When I was in New York City, we used to do a star party in Central Park, and really, we could only see a few hundred stars. I've also done star parties at Bryce Canyon National Park, and there were too many stars to count. The truth is that the human eye can see about 6,000 stars. And that's looking at stars all over the globe. Since you can really only see about half the sky at one time, you really can only see just a few thousand stars. This is one such star field. It features the constellation Orion, and it has two very prominent giant stars. The shoulder of Orion, this red star here, is called Betelgeuse. It's a red supergiant star. And the knee of Orion is Rigel. It's a blue supergiant star. These are stars in their old age. They're on their way to die. And of course, they're going to die by a very spectacular way, a supernova explosion. On the left side of this image, this bright star over here is Sirius. It's the brightest star in the night sky. And it's not an old age star, it's actually a middle age star. It's part of what we call the main sequence. These are stars that are producing energy in what we call the normal fashion. It's a stable phase that lasts, for many stars, billions of years. Stars have a composition of about 75% hydrogen and 25% helium. The reason for this is simply those are the proportions made in the Big Bang. In the Big Bang, the nucleosynthesis, as it forges the elements, creates 3/4 hydrogen by mass and 25% helium by mass. Stars in the main sequence are turning hydrogen into helium. And these are the majority of the stars that you'll see on the night sky. Our sun is no exception. It is part of the main sequence, but it's rather an unexceptional main sequence star. By mass, it's not the biggest. The biggest stars are about 100 times the mass of our sun. And it's not the smallest. Our sun is about 14 times more massive than the smallest main sequence stars. In its energy output, or what we astronomers call luminosity, the brightest stars have a luminosity factor of 1 million greater than our sun, and the faintest are about 1/1000th the luminosity of our sun. The temperature range of stars goes from about 2,000 degrees on the low end to about 50,000 degrees on the upper end. Our sun has a temperature of about 5,500 degrees. This is toward the lower end, and you might be thinking, oh, our sun is below average, but that's actually a good thing, because the most massive stars have a motto of live fast, die young, and leave a good-looking corpse. The corpse, of course, being those supernova remnants produced by those explosions that I talked about earlier. These most massive stars will only live for about 50 million years, not long enough for life to develop on planets around them. Our sun is about 4.6 billion years into an approximately 12 billion year lifetime. And as our evidence, it's long enough for life to develop around it. Now, the most important thing about the sun is that it is our star. Every other star is more than 250,000 times further away than our sun. That means that the sun is the only one in which we can see detailed structure, and we use it as a template for understanding all stars in the universe. For our solar system, the sun can be thought of as the sine qua non, that without which it doesn't exist, because it contains 99.9% of the mass in the solar system. Everything revolves around the sun, both metaphorically and literally, and the energy produced by the sun enables life here on Earth. If something's that important, well, I think we ought to know something about it. So let's take a look at the sun's structure. We'll start with the outer layers, its atmosphere. There are 3 layers of the atmosphere that I will discuss: the photosphere, the chromosphere, and the corona. The photosphere is the visible surface of the sun. Now, the sun doesn't have a solid surface, but it does go through a very strong pressure drop. It goes from 10,000 times the atmospheric pressure of Earth down to 1/10,000th the atmospheric pressure of Earth over a very small radius of the sun. And that is where the surface of the sun is. As I said before, it's about 5,500 degrees Celsius. That is hot enough to melt any known substance. It is also hot enough that the gas becomes a plasma. Atoms are composed of an atomic nucleus and an electron cloud. And when you heat them up, the electrons become dissociated with the atoms. In a plasma, all of the electrons have become totally dissociated from all their atoms. And what you've got is a mixture of atomic nuclei and electrons not attached to any particular atomic nucleus running all around. They're totally dissociated. This is an image of the photosphere of the sun, and you can see it looks relatively calm. It's a sort of smooth yellow ball. You can also see that it has some freckles on it. These freckles are called sunspots. This is a close-up of the sunspot, and this has sort of the classic sunspot circular shape. Looks a little bit like the iris of an eye. Even a small sunspot is rather large on human scales. If I put it up next to our planet, you can see that even a small sunspot is about the size of our entire planet. Some sunspots are much, much larger. Here's a sunspot group that shows a wonderful spiral pattern, rather rare to find one with a spiral pattern, and it is many times larger than our planet. These sunspots are islands of intense magnetic fields. They appear dark not because they are not shining, but just because they are slightly cooler than the surrounding photosphere. They are still very, very bright. It is just the contrast between the much brighter region around them and the material inside the sunspot that makes them appear dark. These sunspot groups can last for months. Much smaller and also shorter lived are granules, which is fine structure on the surface of the photosphere. If I look in closer to the sun, you will see a pattern like this. These individual cells are the granules, and there are millions of them across the surface of the sun. Each of these granules is approximately 1,000 kilometers across. And what they are the tops of columns of material moving up from the interior of the sun, radiating their energy away, and then flowing back down. Each of these granules lasts for only about 10 minutes. So there are millions of them. They regenerate themselves on the order of 10 minutes. The surface of the sun is actually a very active place. Above the photosphere is the chromosphere. And traditionally, the chromosphere was a colored portion of the sun that you could see during a total solar eclipse. Here's an example of that. This is a total solar eclipse when the moon has blocked out the full disk of the sun. And you see that tiny little red region just along the edge of the moon? That was traditionally identified as the chromosphere. But our modern observations have sort of redefined the chromosphere. We have the chromosphere that extends for about 1,000 kilometers above the surface of the sun. We also have something that we call the transition region, which extends for another 100 kilometers above that. In this region, the temperature of the sun rises dramatically. It goes from 10,000 degrees to 1,000,000 degrees. And this is absolutely crazy, because if the energy is being released from the sun at the photosphere, everything should be cooling down. If the energy is gone here, everything should be cooling down as you get further out. Instead, the energy is increasing. Where is this energy coming from? Well, the answer that we found so far is that it's coming from a structure called spicules. This is an image of some spicules on the surface of the sun, and it's taken in ultraviolet radiation. You can see these very thin jets of gas. They only last for about 5 minutes, and the energy is being transported from the photosphere up through the chromosphere and transition region to the corona. The energy is leaking out from the interior, it's creating a shock wave in the chromosphere, and it's driving these spicules. There's a wonderful little movie of these spicules. This was taken by the Stereo spacecraft, and in it you can see these very fine spicules flitting in and flitting out. This is an image taken every 10 minutes for about 1 day of spicule activity. It's very high temperature gas that's shooting up through the chromosphere. But not all gas above the chromosphere is hot. There are also some streamers of cooler gas that appear. And in this image, taken in hydrogen alpha, a specific wavelength emitted by hydrogen atoms, you can see this very long, dark thing here. This is called a filament. And if I zoom in on it, what this filament is gas that is cooler than the material behind it and shows up dark. And it's being held aloft above the photosphere by magnetic loops. And these filaments can last above the chromosphere for several weeks. They appear dark here when they're viewed against the sun, but if they are seen on the limb, as in this image, you can see they are actually quite bright. These are called prominences. Prominences and filaments are really the same phenomenon. One is seen against the disk of the sun and appears dark. One is seen against the background sky and appears bright. The third region of the sun's atmosphere is called the corona. This is a very hot, very low density region, and its temperature is a few million degrees. We really only see the corona well in ultraviolet and X-ray emissions. Its pressure is extremely low. It's down to 1/10 billionth of Earth's atmospheric pressure. We can see the corona with our own eye during total solar eclipses. This is an image of a total solar eclipse, and you can see all these streamers coming out on either side of the sun are part of the corona. It's a rather wispy region, and that extends to several solar radii. The material here is flowing outward and eventually becomes the solar wind. The physics of the corona is dominated by magnetic fields, and that's in contrast to the photosphere and the chromosphere, where gravity dominates. When you saw those spicules created, They fell back due to gravity. Everything in the corona is generally held up by magnetic fields or pushed out by magnetic fields. And you can see that in this image, where I show you coronal loops taken in the ultraviolet. And the plasma here, incredibly heated plasma, is arcing high into the corona. It's heated at the base and streaming up through the magnetic fields back down to the sun through about 500,000 kilometers. The corona is also the site of many storms and eruptions, but we're not going to discuss those today. Those are part of a later lecture. So now we're going to turn inward and look at the interior structure of the sun. The internal structure of the sun also has 3 layers. There's the core, there's the radiative zone, and there's the convective zone. Each layer is defined by how it transports energy. To understand this a little bit, you have to get down the concept of hydrostatic equilibrium. And it's not a difficult concept. It's really just the balance of forces. Gravity is the major force pulling down on the sun. The sun is incredibly massive, and all that mass presses down towards the center and creates a huge force pushing towards the core. What pushes back? Well, thermal pressure. When you heat something up, it creates a pressure. You may remember the ideal gas law from your chemistry courses in high school. Increase the temperature, you increase the pressure. This is the balance going on in the interior of the sun. Gravity pushing down, thermal pressure pushing out. We also have to think about heat transfer. And there are 3 ways that you transfer heat: conduction, radiation, and convection. And you can understand all of those by thinking about your stove. If you've ever touched the burner on the stove and gotten a burn, that's conduction, when heat flows directly from one substance to the next. If you just hold your hand above the burner and you can feel the heat radiating off of it, that's radiation. If instead you put a pot of water on your stove and you bring it to just before a boil, where you can see the water rolling, it's heated at the bottom, rises to the top and releases that heat, that's convection. So this is the internal structure of the sun. It basically is very simple. The core occupies the inner 20%, the radiative zone goes out to 70%, and the convective zone is the last 30%. In the core is where the sun does all of its energy generation. It's at a temperature of 15 million degrees. It contains about half the mass of the sun in that small core. It creates all the energy that then diffuses out through the other zones of the sun. The radiative zone is a relatively calm region because the energy is transported by photons. It is in hydrostatic equilibrium, so material isn't moving back and forth through the radiative zone, just the energy is flowing through the radiative zone. And that energy takes tens of thousands of years to cross the radiative zone. Why? Well, because the photons are doing what we call a random walk. The photons that are emitted from the core travel out and they're quickly absorbed. And then they are re-emitted in a random direction and they're quickly absorbed. And they're re-emitted and absorbed and re-emitted and absorbed and re-emitted and absorbed. And they go off in these random directions and slowly diffuse through the radiative zone. I've seen estimates that say it takes between 30,000 years to 170,000 years for a photon to travel across the radiative zone. In the radiative zone, the temperature starts out at the 15 million degrees of the core and cools down to about 2 million degrees. On top of the radiative zone is the convective zone, and this, in contrast, is a very turbulent region. Here is where movement of the gas transports the energy. At the top of the radiative zone, the gas heats up. That heated gas rises to the surface of the sun, it cools by radiating the photosphere, and then cycles back down. It takes about 10 days to rise to the surface. Quite a contrast to the tens of thousands of years it takes to cross the radiative zone you get across the convective zone in a little over a week. The convective zone is filled with large convective cells, but this is not what we see in the photosphere. At the photosphere, we see the tops of much smaller columns. These are the granules that I showed you earlier. In the convective zone, the temperature of the sun drops strongly. Here is a plot of the temperature profile of the sun's interior. And starting on the right, you can see it's very hot, the 15 million degrees in the core. It cools slowly across the radiative zone, and then it cools very, very quickly down to the 5,500 degrees in the convective zone. This shows you the efficiency of convection. It's a very efficient process for getting rid of heat. It also shows you that the convective zone is actually quite large. Even though it only is the outer 30% of the sun, it contains about 2/3 of the sun's volume. That helps it being a very efficient way of transporting heat. Now, you might be thinking to yourself, that's a nice story. Sure, you know exactly what's going on inside the sun. Do you have any proof of it? And previously, I would have had to wave my hands and say, well, we've got these wonderful hydrostatic equilibrium models, all this theoretical stuff, but I don't have to anymore. In the last decade or two, we have a technique called helioseismology that allows us to look into the interior of the sun. Now, you probably have encountered Doppler shift. Doppler shift is a change in wavelength due to motion. You're familiar with it when a car goes by, and it has a high-pitched sound as it's approaching and a low-pitched sound as it's receding. It goes, that's Doppler shift because the sound of the car, the motion, changes the sound of the car as it goes past you. As it's approaching you, it goes up. As it's going away from you, it goes down. Those same sort of acoustical waves, sound waves, occur inside the sun. They oscillate the interior of the sun, and they cause the surface to pulsate. We can measure those pulsations by seeing Doppler shift in the spectral lines of the sun. If you look at those spectral lines will pulsate back and forth with the Doppler motion of these sound waves. Here's an image of a single sound wave mode. This is a mode that is pulsating throughout the entire sun. And the receding portions of the sun are in red, and the approaching parts are in blue. And this wave here oscillates on a period of about 5 minutes. There are millions of other waves that can be detected by a group known as the Global Oscillation Network Group. This is a collaboration of solar observatories spaced evenly across the globe so that one of them is always in daylight and is always studying the sun. We have a large helioseismology consortium that is continuously studying the sun and determining all of these oscillation periods. As I said, there are millions of wavelengths that they have found, each with a different size scale and a different period. And when you've got different wavelengths, they will penetrate to different depths within the sun, and the varying strength of those wavelengths will enable us to determine the sun's internal structure. So we're extremely confident about that story I just told you about the sun's internal structure because finally we have actually measured it. One little note. The sound waves that we talk about in this helioseismology, they're usually damped at the photosphere. And you need that in order for oscillations. You need to have a harmonic between 2 points. But sometimes those sound waves leak through. And that is the leakage of energy that powers the spicules. But the real energy of the sun is down in the core. And that's where nuclear fusion occurs. There are extreme conditions in the core. As I said, the temperature is 15 million degrees. The pressure is 200 million times that of Earth's atmosphere. The density is 13 times that of lead. In those extreme conditions, you can have nuclear fusion. Nuclear fusion goes by a process we call the proton-proton chain. In this diagram, we show you the basics of the proton-proton chain. First, Two protons, or you want to think of them as hydrogen nuclei, join together and become a deuterium nucleus. Then that deuterium nucleus is smashed by another proton and you get a helium-3 nucleus. When two helium-3 nuclei smash together, you get a helium-4 nucleus, or a normal helium nucleus, and two protons come off. The basic result is that 4 protons go into the reaction and 1 helium nucleus comes out. And in that process, occurring at these incredible temperatures, incredible pressures, you can convert mass to energy. This comes through the famous equation E equals mc squared, where E is energy, m is mass, and c is the speed of light squared. You see, the mass of the 4 protons going in and the mass of the helium nucleus coming out are slightly different. The protons weigh slightly more than the helium nucleus. The difference in energy is converted, the difference in mass is converted into energy via E equals mc squared. 0.7% of the mass going into the reaction comes out as pure energy. The sun shines because it is turning mass into energy at a rate of 5 million tons every second. I'm not talking about 5 million tons of protons. I'm talking 5 million tons as that 0.7% that's being removed from the universe every single second. Now that's going to scare you. Wait a minute. How is the sun going to last long with that rate of energy burning? Don't worry. The sun is about 1 billion billion tons. So it's going to last for a little bit longer. Matter of fact, we estimate that about 37% of the hydrogen in the core has been converted to helium by this time. In the nuclear process, you not only create energy, you also give off these ghostly particles called neutrinos. Neutrinos are a particle that don't interact with just about anything. Okay, there are right now probably 1 billion neutrinos passing through my body, and I don't know it. They don't interact with matter at all. But sometimes you can get them to interact. We have neutrino telescopes, and the original neutrino telescope was basically a swimming pool filled with chlorine. And once in a great while, about once per day, a neutrino would interact with a chlorine atom and turn it into an argon atom. And to use this neutrino telescope, what they did is they filtered the chlorine and searched for those elusive atoms of argon indicating an interaction with a neutrino. And in that manner, we're able to measure the neutrino flux from the sun. We have measured it, and we do have evidence of the nuclear fusion processes going on in the core of the sun. So that is the structure of our star. And it is also the structure of every other star. A star may be described as a gravitationally confined nuclear fusion reactor. Gravity provides the force that pushes down. Nuclear fusion provides the temperature that creates the pressure that pushes back. This is the same physical process that occurs in all stars. Matter of fact, the main sequence is defined by stars undergoing hydrogen fusion. The energy is generated in the core, and it very slowly diffuses through the radiative zone, and it's relatively quickly transported through the convective zone. It's radiated from the photosphere, and it takes about 8 minutes to reach Earth. The time scale from when the energy is generated to when we see it on Earth could be as long as about 170,000 years. And if that's true, I got an interesting thought for you. This image is of the Small Magellanic Cloud. It is a satellite galaxy of our Milky Way galaxy, and its distance is 170,000 light years away. That means the light from the Small Magellanic Cloud has taken 170,000 years to reach us. That is the same amount of time that the energy has taken in coming to us from the sun. The energy from our nearest star reaches us in the same amount of time as the light from one of our satellite galaxies. The temperature in the sun decreases from the core to the surface and then increases into the atmosphere. The magnetic fields of the sun provide enormous activity that drive that temperature increase, and even more in the atmosphere create explosions and huge coronal mass ejections. But we're not going to get into those today. We'll get those in a later lecture on solar storms, and we'll just leave the story of the sun there for now. We'll see you next time. Take care.
Ground control to Major Tom. Ground control to Major Tom. Take your protein pills and put your helmet on. Ground control to Major Tom. 8, 7, 6. Commencing countdown, engines on. 3, 2. Check ignition and may God's love be with you. This is ground control to Major Tom. You've really made the grade, and the papers want to know whose shirts you wear. Now it's time to leave the capsule if you dare. This is Major Tom to ground control. I'm stepping through the door, and I'm floating in a most peculiar way, and the stars look very different today. For here am I sitting in a tin can.